Hey guys, welcome back to quantum mechanics. So we've been discussing scattering theory, and I know it's been a while, but let's just go through this real quick. What we did last time. So last time I actually started with a refresher on scattering theory, which was so this is our general picture. Got a target that we're scattering a beam of particles off of, and the main question that we're trying to answer is, what's the probability that given the energy of this beam that we can control and a form of a particular potential here that will detect some particles being scattered from this potential, right, as a function of energy or as a function of angle or what have you, depending on what we decide that we want to do the measurement with respect to. And so the answer to that question is always the differential cross section. And you can, state what the differential cross section is in words fairly simply, and we've done that a few times. So the basic setup is that we assume that there's some total wave function that's made up of an incoming part, that would be our beam, and there's a scattered part. And the incoming part we can always approximate as a plane wave, and it's the scattered part that we're interested in describing, right? That's the part that's going to give us a contribution to our differential cross section. So what we have is we assume that we've got spherical symmetry, and so our scattered wave is going to be made up of outgoing and incoming spherical waves, and those outgoing and incoming spherical waves we can always write in terms of um, spherical Bessel and Neumann functions. And we are always in the limit where r goes to infinity, so we can always work with the simplified form of this wave function by applying that limit. And you find, for instance, that the ratio of the coefficients is just a factor of minus I. And so in the end, you find that you can write the scattered wave as some spherically outgoing wave, which is what we want. We want to keep the outgoing wave part of this expression and drop the incoming wave. Or is that right? Yeah, right. And the other stuff that's inside, that comes from these spherical Neumann and Bessel functions, we can lump together in this thing called f. And f is a function in general of our angular variables theta and phi. And this thing in general, we call it the scattering amplitude, right? So in that case, we can write our wave in a very simple form in terms of a plane wave plus scattering wave plus the something that looks like this, right? So the scattering amplitude times the spherically outgoing wave. And we found a couple of lectures ago that we can actually write the differential cross section in terms of the scattering amplitude, right? So it all boils down to basically computing the scattering amplitude and then taking the modulus squared, and that will give you the differential cross section. And so a couple of lectures ago, we talked about kind of a quick and dirty way to compute a related quantity, which is transition rates, and that's called Fermi's golden rule. And it just involves computing the matrix element of our perturbation, our interaction Hamiltonian between initial and final states, taking the modulus squared, and basically enforcing conservation of energy. Okay, that comes in handy quite frequently when you're trying to do kind of order magnitude estimates. Okay, so last time we had started to talk about how do we compute this scattering amplitude, this function f of theta and phi. And so what we did was we began by stating that we're going to consider a wave packet that's wide compared to the range of our potential, and so we can basically approximate this incoming wave packet as a plane wave. And in particular, we're going to work in momentum space. And like I told you last time, a lot of times when you're doing scattering theory, it's a lot more convenient to work in momentum space, and then in the end do a Fourier transform to get quantities in position space. And the reason we do that is because we basically have control over the momenta of these particles in the beam by dialing up, the accelerator or whatever we're using to accelerate, uh, come up with our beam of particles. I don't know how you want to say it. The idea is that we can control the momentum, so that's why we work in momentum space. And so, in the absence of any interactions, you could ask the question, well, how does this state evolve with time? And we know from last semester that this state evolves with time, even without the influence of an interaction through the propagator, right? So we have this time propagation operator that will propagate our states, and that propagation depends on the Hamiltonian, right? Even in the case of a free particle, there's going to be some time evolution, right? In scattering problems, we're always going to be interested in transitions that occur between the initial time and the final time. And in these types of setups, the interaction time, so the time that the wave or the particle is actually interacting with the potential, is very short, from very, very small compared to the time that it takes the particle to get from our accelerator to the scattering, and then for the particle the scattered particle to get to the detector. So the interaction time is very small, and so we can safely take the initial and final times to minus and plus infinity, respectively. And when you do that of the propagator, so this is all independent of any type of scattering, but when you do that, when you take those limits of the propagator, this thing is called, this is a special quantity in quantum mechanics. It's called the S matrix. Okay, so the S matrix is a quantity that you'll probably see more of when if you take quantum field theory, because it's the main thing that we're trying to compute in quantum field theory, because we're always interested in scattering experiments, and so we basically work. S matrix is basically our kind of fundamental quantity, but this is how it's defined in non-relativistic quantum mechanics. Okay, so we know there's in the absence of any interaction, right? There's going to be some time evolution of the state, but there's also going to be some time dependence that's going to be introduced by our scatterer, right? The thing that's causing these particles to scatter in our experiment. And that's the interesting part, right? If we didn't have the interaction there, then these particles would just propagate in time, and they would just go on down the beam pipe, and nothing interesting would happen, right? What we're interested in are scattering experiments where we can learn, either fundamental quantities or fundamental things about the particles themselves or their interactions or what have you. Okay. And so, as always, our question in these scattering experiments is, what's the probability that we'll detect particles in this direction, and they have some opening angle d omega, right? And it turns out that in momentum space, this is just the probability that our final momentum lies in the cone of this opening angle, right? So in other words, the momentum's pointing in a direction that's going to hit our detector, right, which has this opening angle. And so we can write down that probability, right? So here we're writing down the S matrix. So this is basically propagating our initial state to our final state, right? That's what the S matrix is. But now we've included the part of the Hamiltonian that depends on the potential. Okay, so we'll have some scatterings. And in general, we should sum over, if we want the probability of the particles hitting this detector, we should sum over all possible final state momenta, right? And so that's what we do, right? It's a standard thing that you would do in quantum mechanics. So, so the question is, how do you compute this thing, right? And the way that we go about it is because it is impossible to do this exactly. So what we do is we work under the assumption that the potential is small compared to the non-interacting part of the Hamiltonian, the free particle part, right? And so what we can do is use perturbation theory to compute our S matrix. And the way we can do that is we can make use of Fermi's golden rule. But the first thing that we have to do in order to do that is to replace this sum here, which was kind of a schematic sum, really, because we all know that momenta is a continuous quantity, so we should have expected that this thing really should be an integral, right? So we need to replace this sum with the integration over the final state momentum. So this is just three-dimensional integration over the 3 dimensions of momenta written in spherical coordinates. And this is an infinity. So this is the magnitude. So you integrate over all possible magnitudes of momentum. Okay. And then we can use this together, use our expression for the probability up here along with Fermi's golden rule, right? So Fermi's golden rule tells us that the rate that these interactions are going to happen, or these transitions are going to happen, basically, so a rate is just the time derivative of our probability, right? And if I plug in our expression from Fermi's golden rule, right? So I've got this integration here coming from Fermi's golden rule, and then I can use. So let's see. So I want to do this integration, and I can use the delta function coming from Fermi's golden rule to actually do this integration. Let's see, what am I doing here? Yeah. So I'm integrating over P final, right? So what I'm doing is basically, let's see, what am I doing here? Oh, right, yeah. So I'm doing it. I have to use the trick because this is not just a delta function in PI, or I'm sorry, in PF. It's a function of PF. So we have to use that trick where we when you're integrating over the delta function of a function of your variable, right? So that's what was messing me up, was where the extra factor of PF here went, right? So all the PFs get turned into PIs. I'm going to leave PF here inside this matrix element, but just remember that we did this integration here, and so we expect PF and PI to have the same magnitude. Okay. All right. So next, what we want to do is to compute the scattering cross section. Right. We need the incoming probability in momentum space. In other words, now we have the probability of the rate of these transitions, right? And in order to compute the cross section, we need the incoming current, right? The flux of incoming particles. And we've already computed this thing in position space, and so basically to get it in momentum space, all we need to do is take a Fourier transform. And so when I do that, I end up with just basically just this thing right here, and you can see the volume element coming in from the Fourier transform. And so then the differential cross section is just basically taking the ratio of those two things, right? And when I do that, so I'm writing the differential cross section times this angle, right? And that's what our this ratio is, and that ratio is the thing that we just computed. So it'd be our R that we computed above divided by this quantity. And when I do that, I get this thing multiplying this solid angle, but that solid angle appears on both sides, so I can drop it from both sides, right? And now what I want to do is I want to be able to evaluate this matrix element, right? And in order to do that, I need to insert some position space eigenstates, because V is a function of position space. So that'd be the easiest way to evaluate it. So I'm going to insert basically two factors of 1 on either side of the V using our completeness relation, right? And then what I'll have is on the right, I'll have a R bra being dotted into a P ket, and on the left, I have a P bra being dotted into an R ket. And those two things are just plane waves, right? One's left going, one's right going, or one's out. Let's see, they're spherical waves. So they're, no, these are plane waves. So they'll be going left or right, right? With the depending on the plus or the minus sign. Okay, so when I put everything together, so this is where I've inserted the two factors of 1, right? And V we know is diagonal on this basis, so it just gives us an eigenvalue or a number back out, and then the dot product between R prime and R double prime gives me a delta function. Then we can use that delta function to do one of the R integrations, right? And that leaves us with this quantity. So we have the differential cross section is the modulus squared of this stuff inside, right? And what I've done here is to shorten up the notation because I have these two plane waves. So when I put those two exponentials together, it's going to go like p minus p prime or p prime minus p. And that thing is what we call the momentum transfer, right? So Q here, when you divide that by h bar, gives me what I'm going to call the momentum transfer. And that thing you can actually compute because you know the direction of pi and pf. You know their magnitudes, right? So here's where we can go ahead and compute at least the magnitude of this thing by computing q squared. And just plugging in this expression, so I would get the magnitude of pf squared plus the magnitude of pi squared, and then minus twice the dot product. The dot product, well, first, these guys, the pf squared and the pi squared, are the same, right? Remember, because we did that integration over that delta function, so and it set the magnitudes equal. So what I have is h bar squared k squared plus h bar squared k squared. And both of those are just p squared, right? And then that means when I take this dot product, again, I get h bar squared k squared. And the angle between pi and pf is just our theta angle, the angle in theta where the detector lies, right? And so I can pull out some h bar squared k squareds in a factor of 2, and I end up 1 minus cosine theta. Then I can use some fancy trig function, and I can write this as sine squared theta over 2, right? And my factor of k squared here is basically the energy, right? So it's basically the energy. Or we can relate that to the energy, okay? The important thing is that the differential cross section, its dependence is on the incident energy. So like I said, we can write that factor of k squared in terms of our initial energy and the scattering angle, right? And that's the only dependence of those two quantities in our expression for the scattering cross section, right? Because this guy just depends on the position r. So our dependence on the initial energy and our dependence on angular quantities are inside of this exponential. This guy just depends. It's a central potential, so it only depends on the direction or the distance r. Okay, and so finally we can compare our expression for the differential cross section to the general formula for that we derived a couple times ago, and for the cross section in terms of the scattering amplitude, and up to some phase factor that we don't really care about, we can extract an expression for this scattering angle or the scattering amplitude, and it looks something like this. So it's just that we just take away the modulus squared, and this is what we call the scattering amplitude in the Born approximation. Okay, so this is known as the Born approximation because basically what we've done is we've computed this scattering amplitude to lowest order. Okay, and it's interesting to note that this thing, if you forget about these factors out in front, it looks a lot like just the Fourier transform of the potential. Okay, and because we're only considering spherical potentials, we can always simplify this. So we could go ahead and actually do the phi integration, right? Because the exponential doesn't depend on phi, right? So we could actually go ahead and integrate this thing and get something that looks like this, right? Remember now Q just depends on theta and basically the initial energy. Okay, so that's where we stopped last time, and sorry for the repetition, but I had to go through it again just for my own sake, just to um, get caught back up. All right, so this is in general. Okay, so we've computed the scattering amplitude, or we have an expression for the scattering amplitude to first order, also known as the Born approximation. And let's apply it to a particular example. And that example that I want to consider is a potential that we've seen before. It's called the Yukawa potential. And it's basically a screened, a lot of times you'll hear it called a screened Coulomb potential. And it's a screened Coulomb potential in the sense that if you forget about this exponential, the 1 over r is the Coulomb potential, right? But when you include this decaying exponential, it basically kills off the what am I trying to say? The reach of this potential um, uh, in an exponential way. So it's basically screening the Coulomb potential, so it makes it die off faster than it would have without it. Okay, anyways, it's called the Yukawa potential, and it has uses in nuclear physics and particle physics as well. All right, so let's go. Let me get to back here. So these are our notes for today. All right, so what I want to do is I want to take this guy and plug it into here. Okay, and sometimes it'll depend on the form of your potential. You can work with several different forms of the expression for the scattering amplitude. Basically, what I want to do is since the potential goes like an exponential, I could rewrite this sine function in terms of exponentials, and so that's what I'm doing here, right? And then I can do this integration, either going through and doing some substitutions or whatnot, or I could just go plug it into Wolfram Alpha. Either way is fine. But in either way, you should hopefully get the same answer. So it's going to go something like, so these are all constants, right? And then I get something that goes like 1 over mu naught squared plus q squared. Okay, so q again is our momentum transfer. And so now that I have the scattering amplitude, I can take this thing modulus squared and get the scattering, or get the differential cross section, right? And so that's what I've done here. I squared it, I get this. And then if I want to make, just looking at this, doesn't really tell you a lot as far as like physical quantities, but now we can make that transition back to position space by just plugging in that expression that we had for Q, or Q squared, right? And what we found there was that this thing went like sine squared theta over 2, and that factor of k squared that we can always relate to the initial energy, right? And so you could see that if I take this differential cross section and plot it, for some as a function of theta, we would have some prediction of basically the scattering rate as a function of theta. Okay, so we would be able to set up some detectors and test this, test the form of this guy. The nice thing about doing the Yukawa potential first is, like I said, the Yukawa potential has uses in nuclear and particle physics, but you can actually derive the Coulomb potential or the result for the Coulomb potential by just taking our expression for this guy and just taking the limit mu goes to 0. Right, when mu goes to 0, like I was pointing out, this thing's just the Coulomb potential. Right, so we can go and from our result for the Yukawa cross section, take that limit and end up finding that this thing. So the mu 0, the mu 0 here is going to go to 0, right? And then I can basically rewrite this k squared in terms of p squared, right? And then the p squared I can write in terms of our initial energy squared. And this thing, hopefully you've seen it before, this thing is called, if I can get this stupid thing to get out of the way, is called the Rutherford cross-section, right? And this is something that you probably studied in a modern physics course, or some introductory course to quantum mechanics. All right. So this was a very important result, and you can go off and read about it on Wikipedia or whatnot. But the point is that we started just basically from first principles in our scattering theory, and just by working to first order, we're able to reproduce a result that predated quantum mechanics. Okay, so that's it for the Born approximation. What I want to do now is talk about a different way of approaching scattering theory, a way that's called partial wave expansion. Okay, so just to kind of recap, so what we've seen so far is that we're always interested in potentials that have a central, have spherical symmetry, right? So we're interested in central potentials. And in this case, the scattering amplitude, which in general would be a function of theta and phi, just becomes a function of theta. In other words, there's no phi dependence, so we can go ahead and integrate over any phi dependence that shows up. And we know that the scattering amplitude is going to implicitly also depend on the initial energy, which would make sense. Okay. So we have a dependence. We have this scattering amplitude, which is kind of our fundamental quantity, and it depends on two quantities in some non-trivial way. And so what you try to do in this partial wave approach is to try to split those dependencies into separate pieces, separate factors. Okay, and so that's what we try to do. And the way that you can accomplish this is that by using the fact that anytime you have a function of theta, you can rewrite that as an expansion in terms of Legendre polynomials. All right, so, and this is just to remind you what a Legendre polynomial is. It goes like the 1-0 spherical harmonic with some prefactor that depends on L. Right. So in general, what I'm saying is that we can take our scattering amplitude, which we usually write as f of theta, but we know that implicitly there's some k dependence there, that we can split it into an angular piece by rewriting it as an expansion in Legendre polynomials of the cosine of theta, and the prefactors, or the coefficients of this expansion, which we're going to label as a sub L, carry the k dependence. Right? So if we've split off the theta dependence, there's got to be some k dependence left, and so we're going to shift it into these expansion coefficients. And these guys are going to be the things that we're interested in. They're called partial wave amplitudes. Okay, so we're taking a full wave and basically breaking it down into partial waves. Okay, and these are the amplitudes. So, all right. So what? So what have we accomplished? Well, before we had one expression for our scattering amplitude. We had one expression that had dependence on two quantities, and now we have. Let's see, where am I? And now what we have is we've traded this for one function, or traded it for an infinite number of functions. These guys, so there's an infinite number of these guys, but they only depend on one variable. Okay, so we've basically separated out the theta. We know what the theta dependence is, and now the question is, we want to compute this part of the scattering amplitude that depends on k. Right? The problem is that there's an infinite number of them in general. Right? However, this we're not completely screwing ourselves over, because what happens is most of the time we're at low energies, right? Comparatively, or relatively low energies, And when you're at low energies, what you find is that basically the first few, maybe the first one or two of these guys, are the only important parts. They're the only parts that are appreciably non-zero. Okay, so what you find is that in these cases you can kind of describe in a very simple way the scattering of your particles in terms of just a few functions, a0, a1, and that's typically all you need, and one variable, right, k, right? And the nice thing is that all that theta dependence now is just locked up in a Legendre polynomial, and we know how those guys look. So how is this true? So how is it that at low energy you only have contributions from the first few partial waves? Well, the way we look at this is that so we have a low energy setup. So we have a beam of particles that are coming in at a relatively low energy, and as usual, the spread of this beam in the transverse direction is much larger than the range of our potential, right? And so what we have is you can imagine cylinders of particles here. So a cylinder at radius rho with some thickness d rho, right? And these guys have an angular momentum, right? Remember rho is what's called the impact parameter. And all particles in this cylinder, have an angular momentum, which goes like h bar L, okay? And then just on general kind of dimensional grounds, you can say, well, h bar L is on the order of k times rho, just using dimensional analysis, right? And so if our target has some small range, which we call R naught, and we know that particles that have rho larger than R naught are going to miss the target, so they're not going to contribute to the scattering, then what we can find is that there's some maximum L value, right? There's, because of this expression here, where if I drop these H bars, if there's a maximum rho, then that is going to mean there's going to be a maximum L, right? So that maximum L value is going to be proportional to rho max, and rho max itself is going to be proportional to R naught, the range of the potential, right? And this is what's going to show. This is what's going to allow us to only compute the first, will allow us to get away with only having to compute the first few. Okay. Kind of conversely, it's nice to see that you can, if you were able to measure this maximum L value, it would give you basically you'd be able to deduce the range of the potential, and you'll see how that works later on. So if we have some maximum L value, that means that where am I? I just got lost. Yeah. Okay. So So if we have a maximum L value, right, that's going to mean that the sum. Let me get back to it. Right, so this sum is not going to be an infinite number now. It's going to be cut off at some L max, and the hope is that the L max is not far from zero, right? So you only have to consider the first few L values. Okay, so we've reduced the problem of computing scattering amplitude down to computing these A sub L's, and now we've seen that we only have to compute a few of these A sub L's, hopefully, in low energy experiments, which is what we're interested in at the time. But how do we compute these guys, right? How do we compute these coefficients given some particular potential? And the way we do that is through just through some algebraic manipulations, really, with the expressions that we already have. So let's consider our free particle, right? And we're working in spherical coordinates, and assuming that initially it's in a plane wave. Okay, so this is all the stuff we've done before, right? So we've got an incident wave, which we're approximating as a plane wave, and this plane wave I can write as e to the I k r cosine theta, just rewriting z as r cosine theta. Okay. And what I can do is I can rewrite this thing in terms of Legendre polynomials. Right? So just like I did in general before when I said that for any function you can do this, this is one particular example. So I can rewrite this incoming wave, e to the I kr cosine theta, and as like this. Okay, so here's my Legendre polynomial. And in this particular case where we have a plane wave, this thing, the coefficient, what I would have called a sub L earlier, I can rewrite as a Bessel function, right? It's a Bessel function, and there's this factor I to the L out here, right? And then this 2L plus 1. But otherwise, it's just a particular case of that general statement that I made earlier, that you can always write these functions of k and theta in terms of two separate factors, right? One being the Legendre polynomial and some other coefficient that's going to carry the k dependence. It turns out that the way you go about this isn't important, but if you're interested, you could look in Sakurai. I think he works through it to show you how this is done. Okay, so the important part is that we're able to do this, right? And we're far from the origin, so we can do that trick again where we take a large R limit of this Bessel function. And when we do that, it reduces to a kind of a sine kr over kr, and we can rewrite that sign in terms of exponentials, right? And so what I want to do is take this limit for Bessel function, which looks like this. So this is just this stuff, and I've separated the e to I kr and the e to the plus or minus il pi over 2 into separate pieces, right? But I've just plugged it into our expression for the plane wave, okay? Here's the 1 over 2 ik that's coming from, this thing here, and here's my Legendre polynomial. So this is what we would have, okay? It's a mess, right? But we can simplify it, and then the reason I wrote these exponentials separately is that we can rewrite these guys in terms of cosines and sines, right? So I can write e to the minus I L pi over 2 like this, right? And then when you think about it, L has to take on integer values, right? So this cosine is always going to be 0. And then depending on the value, if it's even or odd, this is going to give me either plus or minus 1, right? This sine function. And so what I have is minus I to the L, okay? So when L is even, I get 0. Or when L is when L is even, let's see, I'm trying to get, when L is when it's even, it's minus I to the L. Okay, sorry, I was getting confused for a second there. And then I can do the same thing for e to the plus I over pi over 2. So in the end, what I can do is pull out this factor of plus or minus I to the L, right? And so I'm going back now to my plane wave expression. And you can see that this minus I to the L is going to kill off this factor of I to the L, just give me a 1. And we have an expression for our initial plane wave in terms of a Legendre polynomial, some combination of incoming and outgoing spherical waves. Remember, e to the I kr over r is like an outgoing spherical wave, and e to the minus ik over r, e to the minus I kr over r is like an incoming spherical wave. Okay, so what is that bias? Well, what it buys us, and let me just skip here to the next note so I can show you real quick. So basically what we have left is this thing here. So this is our plane wave. Here's a coefficient 2L plus 1. Here are the incoming and outgoing spherical waves. And here are the Legendre polynomials. But remember that when we wrote down the total wave, let's see if I can go back here. Oops. When I wrote down the total wave in the very beginning, and where is it? Okay, so we have So this is our plane wave that we just wrote down. We've written it down in very complicated form, but the point is that the scattered wave, remember we've reduced it, here it is, to e to the ikr and f of theta basically, right? And then the f of theta is the thing that we're going to rewrite in terms of Legendre polynomials. And the a sub l's, and the a sub l's are the things that we're after. Okay, so we have the plane wave, we've got that expression for f of theta, and when I put it all together, so here it is. So here's my full wave function. I've got my incoming wave, right? Here's my scattered wave. And now what I can do is I can combine the like pieces, right? So here I have e to the ikr over r, and I can combine it with this piece, right? And that's going to give me this thing, right? So here's my outgoing wave, right? It has a 1 here. That 1 is the piece coming from the initial wave. Here's the a sub l part. That's coming from the scattering, right? That's coming from the scattering amplitude. And then finally, I have my incoming spherical wave, okay? And so this is where we'll pick it up next time. And from here, we'll be able to start to make a connection between this guy and some physical quantities. And I'll show you how we actually compute or come up with an expression for these guys. Okay, so that's it, and that's where we'll pick up next time. And I'll talk to you guys then. All right, bye.